Okay, let's move on to the next topic called the mole. Okay, so we're not going to talk about this cute little furry creature. We're going to talk about the counting unit. So, to begin, let's talk about this thought experiment. Pretend you have a large stack of paper. Okay, suggest a way to count the paper other than one sheet at a time. All right, let's pretend that it's extremely large and that there's no way that you would be able to count all of the sheets of paper one at a time. I'll give you a hint. What if you knew the weight of 100 sheets of paper? Okay, it's 1 pound, and the stack happens to weigh 1 ton or 2,000 pounds. Okay, I'll give you a moment to pause the video and give this a try. And then when you're done, press play on the video and we'll talk about the answer. Okay, so hopefully you got a chance to work on that. Let's look at how we would solve this. Again, if you use the fact that 100 sheets of paper weighs 1 pound, which is a pretty close estimate, and you knew the original weight of this stack, you would start with 2,000 pounds, multiply it by this conversion factor that's given to you in the problem. Remember, dimensional analysis is something we did first quarter. You can cancel the pound unit. As you multiply across, you end up with 200,000 sheets. And the sheet unit comes over here. Okay. So it's a pretty quick and easy way to solve a problem like this. Instead of using paper or anything else, I suppose this could be used for um, those games where you try to guess the amount of pieces of candy in a jar. Okay, that's another application of this. What we're going to do in chemistry is count atoms. All right, atoms are so small that an ordinary sized sample of a substance contains so many of them that it becomes impossible to count. The particles are considered submicroscopic, meaning they're below the microscopic level. So, how do you think we count atoms? Of course, we count by weighing them. Okay, it turns out that 197 grams of gold has 6.02 times 10 to the 23rd atoms of gold. 107.8 grams of silver has 6.02 times 10 to the 23rd atoms of silver. 12 grams of carbon has 6.02 times 10 to the 23rd atoms of carbon. And 58.7 grams of nickel has the same number of atoms of nickel. Okay, you may be wondering how on earth I got those numbers. I'll let you know right now. So this number, first of all, 6.02 times 10 to the 23rd, is called Avogadro's number. And it can be written like this if you really want to, but I'd prefer you use the scientific notation for this, which is 6.02 times 10 to the 23rd. It's often called a mole, abbreviated MOL, right? It's really helpful to take off that E at the end. So if you had 1 mole of any atom, you would have 6.02 times 10 to the 23rd atoms of that element. In fact, if you had this many of anything, you would have 1 mole of that thing. It works very similarly to a dozen being 12, right? It's exactly the same thing, it's just on a much larger scale. I'd really like you to watch this video, so pause this and go ahead and watch that video. It talks about the history of Avogadro's number, how he came up with this concept of the mole. Okay, and then go ahead and restart this video. What if you had 2 moles of something? So let's start with our original number, 6.02 times 10 to the 23rd something. If you were to times this by 2, right, just take the whole thing and times it by 2. The only thing that you would multiply here would be the coefficient out front. Okay, you do not mess with the exponent because the exponent belongs to the 10. All right, we can review that if you need. But what this ends up being is obviously 12.04, right, times 10 to the 23rd. However, this is not correct scientific notation. What you need to do is move the decimal over 1, and it becomes 1.204 times 10 to the, well, we made this leading number smaller, so we need to change the exponent to represent that, and it would be to the 24th. Okay, so if you had 2 moles of anything, you would have 1.2 times 10 to the 24th things. Okay, so how many moles would I have if I had 24.3 grams of magnesium? Well, I'll give you a hint. 24.3 atomic mass units is the atomic weight for magnesium. That is found on the periodic table. Okay, it's at the bottom, right? So magnesium has this elemental box that shows a 12 up here. That's the atomic number. And then 24.3 down here. This is the elemental box for magnesium. This is the number that you're going to be looking for. Okay, that's the atomic mass of magnesium. If you have 1 mole of magnesium, you would have 24.3 grams. So this unit just converts into grams when you're talking about moles. So this would be 1. All right, if you were to double this number, you would have 2 moles. If you were to halve this number, you would have 0.5. And if you were to multiply it by 10, of course, you would have 10 moles. Easy enough. How many grams of carbon would I need for 1 mole of carbon? Okay, so looking back at the periodic table, what we have here for carbon is this. Okay, so we're going to look at this number here. We're going to convert that to grams, and the molar mass is going to be grams per mole. So this would be 12.01 grams. Easy enough. Multiply it by 2, you get 24. Halve it, you get about 6. And then multiply it by 10, you get 120 grams. Easy enough. How much would 1 mole of water weigh then? Okay, this is not an element, it's a compound made of 2 different elements. Let's look at it. Hydrogen has the atomic weight of 1 AMU, right? There's 2 of them in this formula, and there's 1 oxygen, which weighs about 16 AMU. All right, so if you add all of these things together, you're going to end up with 18. But we're representing 1 mole, okay? We're not representing 1 molecule, we're representing 1 mole, so that would be grams. 18 grams is in 1 mole, per 1 mole. And that's your answer. That's the molar mass of water, is 18 grams per mole. Okay, so obviously if you double it, you can just double this number. And if you have it, you can just have this number, like I show here. Okay, easy enough. How much would 1 mole of calcium chloride weigh? So again, this is a ionic compound. Calcium weighs, looking at the periodic table, it weighs about 40 grams per mole. Chlorine weighs about 35.5 grams per mole. But there's 2 of them, right? So we need to add another one, or multiply this by 2. And all of that together ends up being, let's do the math, 35.5 times 2 plus 40 is 111 grams per mole. And that's how much the molar mass is for calcium chloride. If you had Avogadro's number, 6.02 times 10 to the 23rd formula units of calcium chloride, you would see on the balance that it weighs 111 grams. Okay. Of course, you can double this and then you can have it again. I'll show you the math there. Okay. Let's do another one. How much would 1 mole of glucose weigh? C6H12O6. I'll give you a chance to do this one. Pause the video and then play it when you're ready, and we'll talk about the answers. So what we have here is carbon being 12 grams, hydrogen is 1, oxygen is 16, and then you simply multiply these by how many there are. So this would be multiplied by 6, multiplied by 12, and multiplied by 6. Add those up together, and you get 180 grams per mole. Isn't that neat? Okay, this is very powerful, and we're going to use this a lot the rest of the year, so make sure that you understand this and ask me questions if you have any. The last thing that I want to mention, okay, is this roadmap. You could see this as a roadmap. When in doubt, convert to moles. Okay? There's no way for you to convert, let's say, a mass directly to a number of particles. There's no chart that represents those two things, okay? Because everything has a different density. Likewise, you can't convert mass directly to the volume for a gas, and you can't, convert the volume of a gas directly to number of particles. What you have to do is go through the mole. That's what this is trying to show you. Okay, so make sure that you understand this chart. Let's look at this part up here. Okay, this is something we haven't talked about yet. We're not going to talk about the gas laws, but we are going to talk about some gases like carbon dioxide in the future, right? CO2 is a very important molecule. If you were to take the mass, if you were to start here with the mass of CO2, for example, the mass of CO2 happens to be 44 grams per mole, okay? Grams per mole. That's the molar mass of it. If you were to go from 44 grams to moles and then to the volume, how would you do that? Well, you would follow this chart. You would start with 44 grams. You would multiply it by this 1 mole over the molar mass, right? 1 mole of CO2. Let's make sure that we designate it that way. Would be 44 grams, correct? Because we started with 1 mole. That would get you to moles. After this conversion is complete, right? You would have 1 mole. And then the second step would simply be to use this conversion factor, which relates a mole of a gas to its volume, okay, at standard temperature and pressure. What is STP? Standard temperature and pressure would be the temperature part is 0 degrees Celsius, 0 degrees Celsius, and the pressure part is 1 atmosphere. So this means sea level. Okay, so 0 degrees Celsius and at sea level. We're just going to assume that's what it is for all gases in this class. Anyway, it happens to be 22.4 liters. Okay, so that will be our next conversion factor. We take 22.4 liters, and that's 1 mole for CO2. And then you end up with your answer. Of course, you can see that it's going to be 22.4. After you cancel these moles of CO2, you get 22.4 liters. And that's how much space 1 mole of any gas will take up. All right. You'll get more practice with this when we do the mole conversion practice. Okay, down here. That's the practice you're going to do. Make sure that you ask me any questions if you have them. I think this is a pretty important topic to discuss. So thanks for watching this video. Again, email me any questions you have.